Okay, so let's move with that the second part of experiment number 3, that layout physical verification placement and route for design static time analysis of deep flip-flop. Now in this part we are looking for the layout, how we can design that layout. So that layout, just here we are having that the master latch and then slave latch. In the same way, we are not doing that much of the different things, that much of the complex things. We are making it as much as simple. Whatever the connections are given in this schematic, in the same type of connections we are going to implement in layout. Only the difference is that the output of your NAND gate will become the input of second NAND gate. So at this times we are having that two different layer, that polysilicon and metal layer. For that we are using the contacts. Here only one layer we use for that external connections of your pins, that is the metal one, and the output of the input of NAND gate is connected at polysilicon. So with respect to your schematic, we are just having the layout. So let's move for the layout. So first of all, we need the universal gate, that the NAND gates and one inverters. As here we are using that 8 NAND gates and 2 inverters. So we need the same layouts for NAND gate and inverter. So we are having the or we are going to design the first is inverter. So for that we need one PMOS, we need one NMOS. Here we connect their polysilicon with polysilicon of your NMOS and PMOS. We are taking the output at drain, so drain of PMOS and NMOS. Then we will have the source of your NMOS, source of PMOS. We are just keeping the terminals outside or keeping the layers outside for this. Right now we are not doing any connections. Then we will have that the NAND gates. So for NAND gates we need that 2 polysilicon, that's why we make that 2 fingers. Generate this for the, we can say, N type or NMOS. We need the PMOS. This is the PMOS we are having. We are making the common input at gate side. So we are making their common input gate for PMOS and NMOS. Then the output is taken from the drain side of 2 PMOS and 1 NMOS. So as we have seen in that experiment number 2, the same thing we are doing here once again. Check the DRC. Okay, fine. Then for VDD we are taking the 2 outputs, we just take it. For a source, for the ground, we are taking this one. So is that any DRC we check? Yes, no. So if you are looking for their schematic, so we need 1, N1, N2, N3, N4, 4 NAND gate. So first we arrange in the same way the layout, their layout. So this is the first NAND gate, we just copy, paste. Second NAND gate, we just copy, paste. This third and fourth NAND gate here itself. Now we are having that the common clock, and we are having that A and S and R. So here we find this is S, or we can say D and inverted D, or S and R, whereas the output, the clock, the clock input is same. So we are having that one clock, we are making that 1 input of NAND gate of both the NAND gate N1 and N2 are taking common. Let's take this is N1. We can say this is N2. This one is N3 and it is N4. For our understanding, we are considering that is these four NAND gates N1, N2, N3, N4. N1 and N2 are having a common clock. So in the layout also we are making the same common clock. We are making that polysilicon. We are trying to connect common clock as it is not aligned. So with respect to that, the gate we can align it. Fine. So the clock is common. It is connected with the inverted clock. So we need the output of inverter is connected with this clock. Then the output of this NAND gate, the first NAND gate, the output of the first NAND gate is connected to the input of second NAND gate. The output of first NAND gate is connected to the input of third NAND gate. The output of second NAND gate is connected to that N4. So here we are making one change. We just flip the first NAND gate if possible. Let's check, else we will change in connections. So is that any option for the flip? Let's check. Yes, flip and rotate. Yeah. So we select the flip and rotate. We are going for that flip horizontal and we select this. Yes, we have taken the output. So output and input are nearer for this. So just for that we change it. Then again go to that edit, flip and rotate, flip horizontal. We just flip this. And right now we are try to connect it. We can check their DRC, no error. Okay, fine. So this output of this one becomes the input of next N1, output becomes the input of N3, N2 output becomes the input of N4. Polysilicon for the clock, common connection. That's fine. Then output is metal from the drain connections. Here also output is metal, whereas the input is polysilicon. So for that we need the contacts. So here we take that polysilicon output. It should be 2 lambda. We can extend. Okay, fine. We can extend this. That is. For that we need a contact, so we just copy these contacts and keep here. We extend the metal layer for this. Let's check, is that any DRC for this? Yes, what the DRC, the extra poly around the contact. So we need the extra poly around this also. Fine. Now check it. Yes, there is no error. So we just do the same copy for the N2 and N3. Okay. So this connection is done. Then clock is done. The output of N1 becomes the input of N3 and so on. Right now, the output of, you can go for this. The output of N4 becomes the input of N3 and output of N3 becomes the input of N4. We have to do this connection. So the output is here. So we try to connect with this. This is one of the input. So we are taking the output from this drain. We just carry out here. Okay. Then we extend this polysilicon. We, as good designers, we need that laced polysilicon here we have to use, but at the same time we have to avoid that capacitance when we are having the two parallel plates of metal is going on. And here we need the contacts. DRC, no DRC, okay fine. So output of N3 becomes the input of N4. In the same way, here you have to go for this also. So we are taking from this. So here we connect the polysilicon through this. We need the contact. Check for DRC, no DRC, okay fine. So it's simply, this is of your input S, it is input R, the common clock of N1 and N2. The output of N1 becomes the input of N3. The output of N2 becomes the input of N4. The output of N3 becomes the input of N4 and the output of N4 becomes the input of N3. So this is done. What next we want? We have to keep the same latch. We have to keep the same latch to next one. So here we do the same copy. We are doing the same copy for slave. So we are doing it same copy. As to avoid the error, DRC error for anvil, we need to 11 lambda apart. So let's check. Yes, there is no. Now the output of n3 becomes the input of n1 dash, we can say. So we extend this metal, so output of master becomes the input of so input of this one, we are just taking this. Extra polycyclic bonds we need for contact. Let me connect here the contact. Again we are doing the same thing, copy this contact and place here. Fine. Check the DRC, no DRC. Same we copy for the output of this one. Output of n4 becomes the input of your n1 dash. No DRC, fine. That's great. What next? We have done this, we have to take the output is here. So let's go back to this. Now the input of n1 that and input of your n2, it is inverted, so we need one inverter is here. So we already having one inverter, so we have to just connect the input of that. Okay, that there is a common D input is going to that same inverter, and the output, this output of inverter becomes the input of second. So let's try for this. So inputs are common for them. Output of this becomes the input of, so we are trying to copy the same as we have done for this. We don't need this metal layer, we just extend this. Okay, better way what here we can do this. Fine. Now we have to connect the same input for both. So we are trying to extend this polysilicon on here. Do the connection of this polysilicon input with this. We need 2 lambda. Okay, that's fine. Great. Is that in DRC? No DRC, we find it. So the input, same input, the output of inverter is connected with this one. Now one thing is remaining, that the inverted clock. If here we have to connect the inverted clock, and here we have to connect the same clock. So again, we are taking the same inverter, we are going to design, else we can just copy this one. The clock should be here common. Okay, it's something wrong, so we can design for this. We are taking one PMOS, one, sorry, for we need only one gate, so finger should be one PMOS. We need one NMOS. Here we can just flip because we need the output side at this side. It is inverted clock, so we are trying to flip it. Flip, or also you can first do the connection and then you can flip, no problem. So we are connecting the polysilicon with polysilicon. It is not aligned, so try to align it. It's aligned. So connect their drain connections. This for VDD. Try to work in zoom in, else we can mismatch the layer. Fine. So you can just flip this, as we need the output at this end, so we just flip. Fine. We need the same clock here. So we connect their polysilicon with polysilicon. We just manage the VDD for this. Okay, fine. It's fine. As we are going for the positive clock trigger or positive edge trigger, so we are taking here the positive clock for the second latch and the inverted clock for the master latch. That's all. So the output of this inverter is becomes the input of this input of master clock. So we are trying to take out the output from this. And here we have the clock. We are having polysilicon for the common clock for N1 and N3. extra polysilicon we need for contacts. Then there we need contacts. Sorry. Okay, fine. Let's check any RC node. Okay. So this is overall connection is done. You can once again cross check by electric node. So we are having the electric node. First we check this is input D. Then the output of inverter becomes the input of N2. The clock is inverted clock. So the same clock is given to that slave. Then the output of first N1 becomes the input of N3. Output of N2 becomes the input of N4. The output of N3 becomes the input of N1 dash. At the same times, for storing element, it becomes the input of your N4 and vice versa. Okay, and this is same as it is copy paste, so it is same. So now when we are going to provide the sources, so we have to just take a note that anvil should be connected with VDD. So as here VDD, so we can make their VDD, all VDDs are common if possible. So we are trying to make it common for all. This for positive rail. Is it possible for the ground? If possible, yes, we can do it for this. Just for intermediate, if it is possible, then we can do it. Else, if it is overlap the same metal layer, so we are not making it. So here VDD ground, for this ground we have to mention separate because here that overlap. So to avoid that overlapping also you can use that metal 2, metal 3, metal 4, metal 5 layers are there. Just for simplicity we are not using it. So we are just providing here that VDD and ground as per your connections. So here we are going the VDD, then for both anvil we are connecting that VDD. It is also VDD is there. For lower anvil VDD, this anvil VDD, here also we are providing that VDD, as well as the source of inverter and MOS. Then provide their ground. If you're missing anything, so we might not get that a proper output waveforms. So do it carefully, the connections for that. So I hope so that all ground and connections are done. Then we just provide their input. So we provide the input as clock. So this is the D input. We are having a clock. We are providing the actual clock to slave on this polysilicon. So we are saying the clock CLK, and output we have taken the output from N3 dash. So output visible node at the output of this. So that is Q. Before going to run, we just save the file as save as experiment number 3 layout, exp3 dff layout, and we try to run it. Check it, what happened. it goes on output every time, so we are getting the output high. So we have to just change their clock. If possible, we are making that slower clock. At every time it's 1 as the rising age of the clock. Every time the rising age of the clock, we are having a 1. Let's check the output.